If one wants to calculate the seepage volume flux into a polder in square meter per day, there are two routes one may take. In my book, there is a worked out example of determining the seepage volume flux for an infinite polder using both methods. Here I will discuss the steps to be taken for a finite polder. Please regard C1 and C2 as known values already obtained by having inserted the boundary conditions. The easiest solution probably is the horizontal solution. Recognize that as groundwater flow is steady or stationary, the vertical water seepage in square meter per day must be equal to the horizontal volume flux in square meter per day entering the leaky aquifer at axis 0 plus the horizontal volume flux in square meter per day entering the leaky aquifer at axis L. Here we have the Darcy equations for water entering at axis 0 and water entering at axis L. Please recognize that as water flow is to the left here, your answer will be negative. And if you want to know your total seepage into the polder, you have to add the absolute values, thus the positive values together. The hydraulic head is stated here. When you differentiate this, you get the hydraulic gradient. Insert 0 in this equation and you have the hydraulic gradient at axis 0. Insert for XL into this equation and you have the hydraulic gradient at axis L. And then again, add the absolute values together and you will find your total upward seepage into the polder in square meter per day. Your answer can be in minus lambda divided by C times this term or minus KD divided by lambda also times this term. And these terms are related to each other and you can see that here lambda is the square root of KDC, so lambda squared equals KDC, so this is the relationship between lambda divided by C and KD divided by lambda. Another solution would be the vertical solution. This is another way for determining the vertical upward seepage into a finite polder. You do this by stepping up from the volume flux density, small qz, in meter per day. This is the volume flux density through the confining layer, and you step up towards your volume flux, your upward seepage in square meter per day. And as you can see, this is done by mathematical integration. As you want to know the upward seepage for all of the polder, you must integrate between the bounds of 0 and L. You insert the Darcy equation into this integral equation. Of course, your Darcy equation as its vertical flow, you write in this shape: the vertical volume flux density equals minus the vertical hydraulic conductivity and then times the hydraulic gradient through the confining layer, which is the hydraulic head to which the water is flowing. So that's your artificially maintained level in the polder, minus the hydraulic head from which the water flow dispatches in your aquifer. So that's this H. And then you divide by the distance. And as water is flowing upward, this distance is a positive number. So you insert this into this equation, and this is what you get. And if you integrate between these two bounds, and you insert for H this equation, or likewise for HA minus H, this equation that's doing the same thing, you will find this as an answer. And it's the same answer as we found by using the horizontal solution. Analytical solutions to groundwater flow problems are especially useful as they provide a quick first estimate to many groundwater flow problems. But always be aware that in practice there may be complicating factors, as for instance is evident from this picture, where a shallow rainwater lens overlies saline groundwater with a brackish mixing zone in between. and where also the saline groundwater is shown to be reaching the surface water by upward seepage along a preferential pathway. A problem is upward seepage of saline groundwater that may be further enhanced by future sea level rise, as this will cause an increase in this upward seepage into our polders. Preferential pathways for upward seepage are especially evident from this picture that shows different types of boils in deep polders. A pin boil, a sand boil where sand is transported upward with the water flow, a boil emitting naturally occurring methane, which is, as you are most probably aware, a most potent greenhouse gas in the Earth's atmosphere, thought to heavily contribute to the enhanced greenhouse effect. A sand pseudovolcano, a collapsed ditch bank, holes in the ice caused by warmer water welling up from a boil, sand boils on land, and here we have a schematic diagram of boils showing several subsurface conduits or preferential pathways.